Welcome to MrCScience.com's video on atomic structure and the periodic table. We're going to talk a little bit more about the periodic table of elements and what the different numbers on there mean and what you can derive from there. This is the beginnings of how atoms go together to form molecules, so some interesting things. Let's go ahead and take a look at the periodic table. Okay, so this is a periodic table of elements. We've looked at before. We've talked about the different colors, meaning nonmetals and metals and transitional metals and so forth. Now we're going to talk a little bit more about what these numbers mean. So I pulled carbon out of the periodic table of elements here. And so C, its elemental symbol is C for carbon. On the top is what's called the atomic number. And on the bottom is what's called the atomic mass. So let's talk a little bit more about that here. Let me grab my pen. So in the 6 right here is the atomic number. And that 12.0 there is atomic mass. Now sometimes when you use different periodic tables, this number, the atomic mass, might be different. This is always the same. So, you know what an atom's made out of, correct? In the center of the atom, you got protons and neutrons. And orbiting around the atom, you have your electrons. Okay, so your atomic number stands for the number of protons. So I like to use, this was pound or number long before it was ever hashtag, so we're not doing social media hashtag protons. No, this is the number of protons. So a carbon atom has 6 protons. Okay. Electrons, for right now this is a lie, but we're going to say the number of electrons always equals the number of protons, so it's got 6 electrons. Now the atomic mass is a little bit different. Atomic mass equals the number of protons plus the number of neutrons. So how many neutrons does carbon have? Well, it has 6 protons. It has 12 total. So 12 minus 6, we have 6 neutrons. Oops. Lost my pen. There we go. 6 neutrons. Okay, so atomic number 6 means 6 protons. Number of electrons is the same. And then number of neutrons is that atomic mass minus the number of protons. So that's the number of protons and neutrons. Let's try a few of these just to get the idea. Okay, so I've pulled 3 elements out of the periodic table here. We got potassium, cobalt, and chlorine. So let's figure out how many protons, electrons, and neutrons are in each of these. So let's do the first one together. So the atomic number on top stands for the number of protons. So this has 19. What's up with my... Okay, that fixed it. So 19 protons. So let's grab our pen tool again here. 19 protons. So how many electrons does it have? Well, electrons equals protons in this instance. So we got 19. We'll talk about ions later when that changes. Okay, so neutrons. So we've got 19 protons, we got 39.1 here. Now you can't have 0.1 of a neutron, so we're always going to round. So we're going to take 39, oops. This is really getting annoying. There you go. 39 minus 19 equals, we've got 20. So we've got 20 neutrons. My pen is not behaving itself. That is an absolutely ugly 20. Okay, so 19 protons, 19 electrons, 20 neutrons. Okay, see if we can do cobalt. Remember atomic number, atomic mass. Okay, if you did cobalt, number of protons, easy is the atomic number. So we got 27 protons. And my pen does not want to behave. Hey, we got a French 7 there. Okay, so how many electrons? Well, easy, 27. Okay. Electrons, 58.9. We're going to round that because we can't have 0.9 of a neutron. We're going to round that up to 60. So we got 60 minus 27 and do all that together, and you've got 3 and how come I can't think? 33 neutrons. In this class, although simple math shouldn't be that hard, and if I can write a 3, 33 protons or neutrons, you can use calculators in this class. So now let's talk about this one. Protons for chlorine, 17, because its atomic number is 17. And I'm going to have to fix my pen problem. Electrons the same, 17. There we go. Protons, now we're right in the middle, 35.5. What we're going to do is round. What's going on here is we have something called isotopes. An isotope is where different atoms of chlorine will have a different number of neutrons. So right now for this we're going to round, so we're going to go 35.5 to 36. 36 minus 17 is 19. So we got 19 neutrons. And my pen isn't working. There we go. 19 neutrons. So that's isotopes. So let's talk a little bit about isotopes. Okay, let's take an element well known for its isotopes. Uranium. Uranium U. So uranium, based on what we see in our periodic table of elements here, how many protons does uranium have? Well, it has 92, same as the atomic number. How many electrons? You may be wondering, why is electrons always written with a lowercase e here? Well, electrons generally is represented as this, just a lowercase e, so I often write it that way. So electrons and protons in this instance are equal. Remember, we will find a time when they're not. So 92. Neutrons, well, let's take let's do it the quick way. In chemistry, you're allowed to use a calculator. So let's take our 238, which is, our 238, which is our atomic mass, and let's subtract our number of protons of 92, and that gives us 146 neutrons. Okay, now this number, see this 0.0 here? If you look in at other periodic table elements, sometimes it'll be 0.075 or something small here. So this is an average of all the different types of uranium. So the uranium here we listed with 146 protons, so atomic mass of 238 is called uranium 238. It's written like this, 238 in front and U. So it's in front, up above and in front is that. If it's down here, it's the number of atoms. So they're not 238 uranium atoms here. This is uranium with a mass of 238. So that uranium 238, if you take a natural uranium sample, you'll find generally 99.3% of the sample will be uranium 238. Okay, there's another isotope of uranium that has a mass of 235 or 146 neutrons. That's uranium 235. Uranium 235 makes up about 0.7% of natural ore. Then there's another uranium 234, one less neutron, and that makes up about less than 0.01% of natural uranium ore. Now, chemically, all this uranium behaves the same, but radioactively, how its nucleus behaves is slightly different. All three of these are isotopes of uranium. Okay. They all are chemically the same. The only difference between them is mass. Now, what's interesting about this is the one they cared about. This is the one used in making nuclear bombs. So, in World War II, they had to figure out how to get the uranium 235 at a much higher percentage than 0.7% in order to create a nuclear bomb. There's some interesting documentaries on that you can look up if you want. But the only difference between them is mass. So they set up. You can use centrifuges. You can use beams of atoms and deflecting them, things like that. But just based on mass, they were able to increase the amount of 235 by pulling that out of the ore and getting rid of some of the 238, and from that they could make their bombs. So this is isotopes. Isotopes are chemically the same. They're all uranium because what makes it uranium is the number of protons in the atom. So that decides which atom it is. And then this number of the neutrons just add mass. So this is just uranium 238 is slightly heavier, three neutrons heavier than uranium 235. You're going to read a little bit about how they figured out that the atom was laid out with the protons and the neutrons in the center, protons and neutrons, and the electrons orbiting around the the atom. So instead of what they call the plum pudding atom model, where they were all mashed together, all kind of equally spread out. If you have any questions on this, always feel free to drop me a line at mrc@mrcscience.com.